Hi, everybody. Thanks very much for coming. I'm very happy to be able to introduce today's speaker, who is Vivek Chaurasia. Vivek did his master at the University of Mumbai, but finished with a master thesis with Professor Mark Hannam from Cardiff University. And then he moved on to Vienna in Germany to do his PhD with Professor Bernd Brückmann. And currently he's a postdoc at Stockholm University. And so please, Vivek.
Thank you. Thank you for the introduction. Yeah, so I know a few people, but I don't know many people here. So hi, I'm Vivek. And yeah, like already Alex introduced. So like here, I want to present some progress with simulating black hole neutron star systems with the BAM code. And this code is like a numerical relativity code, which was developed in Vienna in Ben Brugman's group, and to which David here also has contributed during its crucial development years. And so currently BAM is also part of a larger collaboration called the Core Collaboration. And it stands for computational relativity. And it has researchers from a lot of different countries, so Germany, then from Brazil, US, and David, and also Hannes Rutter, who's from Portugal, and then myself working from Sweden. So this is a very international collaboration, and in this collaboration, we are mainly concerned with simulating neutron star mergers. However, there are like other versions of BAM code which are used for binary black hole simulations. And this is mostly in Mark Hannam's group, where I did my master's thesis part of it. And also by Sasha Husha, who's in the Balearic Islands in Spain. So with that, I'll start. And basically, I'll talk about some interesting properties of neutron stars and why we are like really investing so much time and energy to really understand that. So as we all know, that these are possible end state of stellar evolution, and also one of the most compact objects that stellar objects that we know. And if we were to compare a typical neutron star to an average sized city here on Earth, then it would look something like this here in the picture. And here you have a typical neutron star, which is like 20 kilometers in diameter. And it, as you can see, it fits right over Stockholm County. So it's not a very large or stellar object. And then its density is also at the very extreme side, which is like 100 million tons per cubic centimeter. And if you want to compare, then you can think of iron, which has a density of 7.9 grams per cc, or the densest material on Earth being osmium, which has a density of 22.6 grams per cc. So you can imagine that how dense this matter is. And then being such dense matter and really compact next just to black holes, it also has a very extreme gravity. And it is of the order of 100 billion times that of Earth's gravity. And owing to some such extreme properties of matter and gravity, the only way to understand such compact objects is to use full set of GR equations. And especially in the case of two-body or multi-body interactions of such system, one has to solve this set of equations without any assumptions. And this is done via the field of solving them numerically, so numerical relativity. So next, here I have a slide on binary neutron star mergers. And binary neutron star mergers are really interesting systems because one can study their gravitational wave emissions, and also such systems are expected to eject a lot of matter when they collide, which then powers kilonova and gamma ray bursts. So they are really interesting systems. And here I have a movie from, so this movie is a simulation of a binary neutron star merger, the event GW200105 and this simulation was done using BAM code. And so basically, as we all know, like this was the first detection of the binary neutron star system, where we detected the simultaneously gravitational waves and electromagnetic countercurrents, and also gamma ray bursts from the same event. And here in this movie, you see like the gravitational wave from light yellow to red, increasing in strength. And then you also see the neutron star matter, which is shown here in light blue to dark blue. And here the density ranges from 200,000 to 600 million tons per cubic centimeter. So it's really dense, this event. And here the neutron stars are asymmetric, so they have a mass of 1.55 and 1.22 solar masses. And once the system merges, then it also produces ejecta, like some unbound material. And here in this movie, it's shown in the purple color. And this ejecta is the source for the kilonova that was detected during this merger. And as this merged system emits additional gravitational energy and also angular momentum, it settles down to a black hole, which you will see here in gray. And then it has some disk. So, and here you have the gravitational wave strength from the system. And so what LIGO measured was the pre-merger signal, and the post-merger signal is not currently in the band of the sensitivity of ground-based detectors. So next, okay. So next I want to talk about BAM, which makes and such codes which make it possible to do numerical relativity and really solve these equations without really assuming a lot about the system. And so BAM in that respect is a finite differential code, and it has a high resolution finite differential stencil, which is 6 to 10th order. And basically this finite difference is used to approximate the spatial derivatives of the fields in GR. And then you also have high resolution shock capturing scheme, which is used to capture shocks which can be formed in the violent merger scenarios of neutron star mergers. And then such systems have a wide scale that at which physical processes are happening. And so for that to capture different length scales and time scales of the physical processes, we also need to have like adaptive mesh refinement. And so in BAM, we have a mesh refinement mesh shown here in this schematic. So basically, BAM has a box-in-box mesh refinement. And here you see that as we go towards the inner levels of the refinement, then we have a increase in the resolution of the grid by a factor of 2. And as you approach the compact objects, so you will have the highest resolution for the simulation. And each of the compact objects can be covered by highly resolved grids. And these grids basically track the matter motion and also the black hole motion across the grid. So this is like an important aspect of like being able to do full GR simulations. Then, because we all have such, I mean, a lot of these simulations require computational resources, a lot of computational resources. So basically, the whole computational grid is like divided into these chunks, and then an integer number of these chunks are then given to MPI processes which handles them. And so we have in BAM a hybrid parallelization scheme, which is MPI and OpenMP. So each of these, an integer number of these chunks are handled by these MPI processes. And then we have each individual MPI process can have lots of threads which work on. So with such a strategy, we are able to scale up to 10,000 cores. So we are able to use these many cores efficiently for doing numerical simulations. And then some of the typical BAM statistics for simulation can have numbers like this. So for each simulation, you can have 230 variables every grid point. So at every grid point, you have these many variables. And then in a medium to high resolution simulation, you can have 10 million grid points in a 3D simulation. And then at every grid point, every time step of the evolution, it performs 20,000 floating point operations. And it can be a bit more depending on how many different kinds of physics that we're talking about. And then medium to high resolution simulation can take half to 1 terabyte of RAM, which includes MPI communications around these divided chunks. And then the output from such simulations can be of the order of a terabyte. And this includes like 3D output of useful variables that help us in extracting useful physics from them. So BAM is not the only code out there, and there are other codes, and these codes can be classified into grid-based NR codes and particle-based NR codes. So grid-based NR codes, you have like the spec code from the SXS collaboration, which is a spectral Einstein code. And basically it uses spectral methods to evolve the field. And then you have CENTRA code, which is from Masaru Shibata. I was told that he was just giving a talk last week. So his group has this code CENTRA, which is again a finite difference code. And then we have an Einstein toolkit, which is publicly available. And it's also a finite difference or finite volume. And then most recently, we have this here Athena++ code from Sebastiano Bernanke's group. And then for the particle-based NR, so the idea is very interesting. So you have all the geometric variables of GR, which are put on grid, as I showed here. And then the hydrodynamics of the system, when you have matter fields, can be formulated in terms of smooth particle hydrodynamics. So this is a very new approach, and is being pursued by Roswog and Dina. And Roswog is currently my boss in Stockholm. So this is like the overall feature of BAM and some other codes out there which perform such NR simulations.
You said that you can go up to about 10,000 cores.
Yep.
Do you actually go up to 10,000 cores in a typical simulation? It seems like a lot.
So yeah, that's good. So these are from scaling plot numbers.
Yeah, so what's the real use case like?
So like about 1,000, 2,000 cores. Yeah, but yeah, like I said, that these are more from the scaling plots. Mm-hmm. Right. So moving on ahead. So here I'll just talk a few of the equations that are being solved by these codes. And these are not all the equations or all the formulations that I'm going to talk about, but there are a lot more. But the important one is, so the idea of an NR code is to solve this equation. However, in the form it is written here, this is in a covariant form. And so as such, it looks beautiful, but is not like useful in solving it numerically. And so this has to be now transformed into the language of partial differential equations, which we understand how to solve. And that is done using the 3+1 decomposition of the 4D spacetime. And basically the idea is here that you foliate the spacetime at constant temporal slices. So you get 3 spatial hypersurfaces and along the constant time surfaces. So once we do this 3+1 decomposition, we get 2 sets of equations. One is the constraint set of equations, and the other set is the evolution set of equations. And if you want to, like, there's an analogy within electrodynamics, like Maxwell's equations, where you also have like constraint equations and evolution equations. And so you basically get something like that. But so again, just to note, these equations are not directly in the 3+1 median form. So the constraint set of equations are are written in an elliptic form here, like at least the first equation. The second equation has some free degrees of freedom, after which you can get an elliptic form of the equation. And so this set of equations basically have their own solvers to solve. So elliptic equations are solved iteratively. And and the elliptic equations are what is being solved by codes like BAM and SPEC or other codes. So, but these evolution set of equations, they require initial data. And this initial data is obtained by solving the constraint equations on the initial hypersurface. And once we have initial data from this, then we can supply and evolve the system using these set of equations. So just to mention here, this set of equations is one formulation of the evolution equations, which are the Z4C equations. But these evolution equations can also be formalized in BSSM, or there's another FFC Z4, which maybe David can comment. Yeah, so the reason to use Z4C is it is numerically very stable system of equations to solve. And then it has very interesting property, which is called constraint damping property, which is very useful. And the idea is that, so in an ideal world, we solve constraint equations, use the initial data in this, then evolve to the next hypersurface. Then we should again solve these elliptic equations so that we know that, yeah, these are constrained. However, in reality, we don't do that because it's very expensive solving elliptic equations at every time slot. So what we do is we follow a free evolution scheme. So in a free evolution scheme, we just solve the initial, follow initial data at an initial hypersurface, and then use the evolution equation to evolve it. But we have some checks such that we say that the constraint violations are minimized. And this property is like works best for the Z4C formulation. And this is one reason why we in BAM want to use Z4C formulation, so that yeah, we are still solving Einstein's equation. So okay, next moving on to other set of equations that have to be solved when you have matter fields in this spacetime are the equations of general relativistic hydrodynamics. And again, here the equations are in covariant form, and one can go through a similar procedure of 3+1 decomposition, and then come to a partial differential equation set as shown here. And these are in the so-called Valencia formulation. So basically, these are the equations of motion for the matter fields. And these have to be solved in conjunction with the other equations that I showed before. And basically to understand the dynamics of the system. And an important ingredient that I have not explicitly written here is the equation of state of the matter field. And especially for neutron star, it is a very crucial piece of information that goes in the system, because this is something that we want to extract from these detections of gravitational waves and electromagnetic particles. So basically, an equation of state also goes here, and also additionally, it closes the system of hyperbolic equations. So once we have all of these equations, we have the infrastructure. Then next, an important outcome from BAM simulations has been the first public database of binary neutron star merger waveforms. And this was the first database that was released in 2018. And it had like 164 physical systems. So you vary different parameters of the binary neutron star space, and then you get different physics out of it. And then each of these simulations could be done at different resolutions, because this is one thing that should be done by when one is solving numerical, like getting numerical solutions, so that we know that yeah, things are convergent and do not depend on resolution. So we have like 400 of these individual simulations over there. And all of these simulations require 150 million CPU hours to do. So in the database, if we go, then we find interesting cases like a high mass system, where the total mass of the binary neutron star system has been varied to study its effect on the gravitational wave emission, the electromagnetic counterpart, and also the nature of merger remnant. And then we have systems where we have high mass ratio. And here you have neutron stars of asymmetric masses. And then again, we study its effect. Then we have recessing systems where we have like individual spins of the neutron star, which are inclined at some angle to the orbital angular momentum. And then in the database, there's also simulations which capture, which have this dynamical capture binaries. And here, basically, the binaries have very high eccentricities to start with. And here we see that this waveform is uniquely distinguishable as compared to the quasi-circular cases that we mostly like simulate in NR. And then in this database, we also have data from another code called viscity. And this is like, here this waveform is from using viscous hydrodynamics. And so in this database, you also find data from this, and they are also part of this core collaboration. So overall, we have a wide variety of systems that we explore. And we also have currently a second release, which is going to come soon. And this will have 100 plus new simulations. And all of these simulations have required 500 plus million CPU hours to, yeah.
So can you tell me what you mean by release?
Yeah, so this picture I've taken from the database paper over there. And basically in viscity, they so as opposed to BAM, we don't have any neutrino like leakage scheme or anything, whereas in viscity they have. And so this is like what I mean here, that they have leakage scheme for capturing the effect of neutrino emission and absorption. And yeah, but yeah, I mean, I shouldn't have because I have, yeah, everything from them. And so yeah, I mean, so this is like the variety of yeah. So this particular waveform was where they have treated viscous hydrodynamics in the simulation, which is so mostly the equations that I showed before for GHD. There's a like ideal hydrodynamics, but one can also go and do other interesting things.
For instance, well, like viscosity is thought that is maybe for course because it's like a super. So in this simulation, has one effect.
So this is David Radich's group. They do explore a lot of these scenarios. In BAM, we don't currently have that capability that we usually go with the ideal hydrodynamics. But yes, they do explore here. So a good reference would be to look at works from David Radice. And yeah.
Sorry.
Yep.
The final stage is always the black hole.
You mean in all of these scenarios? Yeah. Not really. So if you look at the waveform at the end, sorry, what?
Because the ring down.
Yeah. Yeah. So if you can see, I mean, this is still not emitted in a gravitational wave and like angular momentum. So it still is like a hypermassive neutron star. Same for this. So the reason is like why we haven't seen complete ring down here is because to do that, we will have to continue these simulations for a very long time. And one can really compute the rate of emission of energy and angular momentum and compute approximately how much time it will take to settle down and maybe form a black hole or something. So the simulations where we did have that, you will see that yeah, these simulations don't have that. Okay, so yeah, moving on. I just wanted to show this map, which is a very interesting map of a database. So this was like the first database of finding neutron star mergers, and as I was talking, so in these database we have very many physical systems, and they differ by exploring different range of equation of state, and this goes from soft to stiff. And then in this panel, we see the effect, the simulations that have total masses, which has been varied. Then we have different mass ratio system, then the individual spins of the neutron star here. Then the eccentricity, the orbital eccentricity in the binary system. And then this is the quadrupolar tidal deformability of the neutron star. And then how many orbits we simulate in these simulations. And finally, the resolution that we employ to resolve the individual neutron stars. So this is a very interesting map in the sense, because this is what drives the development of this template wave banks, which then go in the, then being used in the match filtering technique of detections of subsystems. And so such a database from the NR side is a very important thing to have. And for binding neutron stars, we have. But now that we are in an era where we are now detecting black hole neutron star system, such a database will be of a crucial importance to develop gravitational waveform models, and also understand the interesting physics that's happening in this system. So for the rest of the talk, I'm going to present our progress with black hole neutron star merger simulations using DAM. And here is another movie from black hole neutron star merger. And this particular simulation was done for the press conference of the detection of this event, which was the first. And there was another event alongside, but this system here, let me pause. So this system here is close to this merger. So here in this movie, the blue, the blue one is the gravitational wave emission, and then the neutron star goes from light yellow to orange, increasing in density. And as the system evolves, it emits these gravitational waves. And then we see that most of the neutron star is swallowed whole by the black hole. And so here we don't see any accretion disk being formed, or also a lot of ejecta or any ejecta being emitted from this system. So this is also in accordance with what was detected, with no detection of electromagnetic signature from such system. And so in terms of black hole neutron star merger, these are what is called as a non-disrupting system. So a non-disrupting system, the neutron star is wholly swallowed by the black hole, and there is no tidal disruption. The other kind of black hole neutron star mergers will be disrupting neutron star. And basically in that scenario, the whole neutron star matter is kind of smeared out, and then it can form disks and also have tidal ejecta. So
do you need a highly elliptic orbits around the tidal effects and accretion?
you mean here in this? So this is a quasi-circular orbit. This does.
No, what I mean is that you don't see accretion is right there.
Yeah.
But what do you need to see an accretion disk? Highly eccentric orbit?
Right. Yeah. So there are few parameters that are important if we want to have like tidal disruption of the neutron star. One is spin of the black hole. So if it is a line spin, highly spinning system, then this will have more probability of having a strong tidal deformation of the neutron star. Then another thing that is important is the mass ratio of the system. So if the mass ratio of the system is quite high, where the black hole is the more massive object, then it's just gonna be a non-disrupting system. Everything is good. And this signal will be very close to binary black hole mergers. And so one can also analytically or use these binary black hole models to really talk of this non-disrupting system. So to answer your question, spin, like mass ratio, these are like the obvious things. Then you can also think about the equation of state. So how soft or stiff the equation of state is, which would also allow to have disruption. So these are the, yeah, I think what you mentioned about eccentric orbits. So that can obviously also, once the neutron star comes very close to the black hole, it can be disrupted. And this is like also very close to what we studied with binary neutron star mergers in highly eccentric orbits. So as the neutron star comes very close to the other neutron star, it already has oscillations, which gets imprinted on the gravitational waves. But for a black hole system, it could be like disrupted already with the close encounter.
The spin house.
Yeah, the spin, that too, the aligned spin.
It's because you can have like colder orbits or something.
You mean, okay, the reason about this, so if we look at some of these works, like analytical works of how we can have more tidal disruption, then it is like directly proportional to this black hole spin, which is like just if you want to get an idea of what happens. So there is this the innermost stable orbit, and then you have the disruption radius, and this affects if the black hole is spinning like aligned or anti-aligned. So if it is if the disruption radius is outside this inner stable orbit, circular orbit, then the neutron size will be disrupted. Whereas if it is inside, then it is already in the circular orbit, so it doesn't get disrupted. So that's like, yeah.
That's for the horizon. Like once we reach the horizon, then you can drop. So you have like any object and the horizon, and then you have one time.
So if you have spin, then you say, oh, you're thinking in terms of the Kerr solution, like.
Or you mean like once you reach like innermost stable orbit, you just go in, or?
So astrophysically, you have like you have this this expression that tells you where if you have this tidal disruption, like the disruption radius, if it's outside this ISCO, then already because the neutron star is going to be there, so it is tidally disrupted at that point. Whereas if it is inside the inner stable circular orbit, then it is not going to encounter the disruption radius before entering this, and this is going to be very close to the black hole, so you won't see any effect of this disruption. That's what basically. Right. So okay, yeah, let me. So here, I mean, in this system, we basically don't see any like exciting things that we want to see when matter is ejected or forms an accretion disk. And so in that sense, like non-disrupting systems are very boring, and they can be understood using binary black hole evolutions. So okay, so making such simulations possible, we of course need the initial data. And I was talking, as I was talking about solving these constraint equations. And they can have their own solvers, and they vary on different methods, like how they solve these particular equations. And so for BAM evolutions of black hole neutron star binaries, we rely on the LORENE initial data solver. And then most recently, we have had this Elliptica solver and also the FUKA solver, which is available for this. And so when we started with this project, we were mostly working with LORENE because at that time we didn't have these solvers. So LORENE solver is a publicly available solver which can compute binary compact object initial data. So binary neutron star, black hole neutron star, and binary black hole. and it is based on spectral multi-domain methods. And then it uses these spherical coordinates. So here, each of the compact objects will be covered by spherical grid. However, it was released in 2006, quite old code, and that time it was not parallelized, and is also not maintained. It's really old. So then we have this Elliptica solver, which is recently developed within the core collaboration by Rashti et al. And this is again a spectral multi-domain solver, and uses cube sphere grid for covering each of the compact objects and then decomposing the equations to solve them here. And then it is just thread parallelized, so you can use one node and use all the cores with thread parallelization, and is well maintained because it's quite new. And then we have another FUKA solver, which stands for Frankfurt University Cadence Library. So this is from Philip Grant-Clement and Elias Most, Jens Pappenfort. These are the people who developed this code. So this is again a spectral multi-domain solver, and however this uses another type of grid called bispherical coordinates, and here each of the compact objects are here. Oh, 1 minute. Hold on. So now it is also anti-parallelized and well maintained. Right. So these are the solvers, and one important point from all of these solvers is that when we have a black hole in the system, then these solvers use excision techniques to generate the initial data, which basically means they remove the interior of the black hole and put appropriate boundary conditions, and then generate initial data for this. So now having this excision initial data, but we want to evolve these initial data using BAM. However, BAM and many codes like that, they do not employ this method of dynamically removing the numerical grid, which is pursued by other codes like SPEC. So in SPEC, a binary black hole system would look like this, and as it moves across the grid, the space is dynamically removed from the computational grid. And so this is called an excision technique of evolving, whereas BAM does not have this capability. And so the way we use excision initial data for such systems is that we fill the interior of the black hole with some smooth junk data. So this is basically a data that has been extrapolated from outside the horizon to fill the grid points inside the horizon. And then we use standard puncture gate choices. Now, so BAM-like codes, what they evolve normally is a puncture initial data, where the black hole is represented in this form, like this is written in isotropic coordinate. And then here, there is no active requirement of excising your computational domain within the horizon of the black hole. And it's like excision without excision, but you don't have to actively do this. This is like automatically done by the way this initial data is represented, and importantly by using this dynamically gauge condition. And so this is what we do. So we use this excision initial data from the other three solvers that we have. We fill this and then use this gauge choice. So basically this gauge, this is called dynamical gauge because it actively decides how to slice the spacetime and also tells how the speech of this hypersurfaces is stretched or not. So this is done dynamically during the evolution. And so in this sense also they are like singularity avoiding conditions, which are useful for evolving all kinds of initial data. Okay, so now having this conditioned initial data, we evolve it using BAM, and then we can do code comparisons among other groups which have evolved the same system, but using different initial data and also different methods for evolving. For example, BAM and SXS scrap comparison is shown here. So here like I mentioned, SXS collaboration, they have excision initial data, and they also use excision techniques to evolve their data on the spectral grid that they have. And there's all and then at the bottom we have a comparison with the CENTRA code, which is another code, finite differencing, but again it is built for evolving puncture initial data. And so in both of these comparisons, we find very good agreement here. And in this plot, we also show like effect of resolution, and then how the phase varies among different resolution and with the CENTRA resolution. So overall, we find that the results are comparable with both of these very distinct codes, very distinct evolution methods. And so that's quite good. And importantly, what we want to do is that we want to capture the final phase of this merger very accurately. And the reason is because at that point, the neutron star is being tidally disrupted if it is a disrupting system. And this part of the waveform is going to capture that signature of the tidal disruption from such an event. And this event, like this phase will give us useful information about the radius and equation of state of the neutron star matter, because it's dependent on these quantities. And then also overall, we want to have accurate gravitational waveforms, as in the case of binary neutron stars, because especially for black hole neutron star system, many groups are pursuing to infer Hubble constant from black hole neutron star mergers. So that'll be very useful to have this done accurately. Okay, yeah, I think some more. Yeah, I think I will just go. So I was talking about this filling of the black hole interior and then evolving it using scientific. So here I have a plot which shows how the constraints are behaving. So this is here what we show here is a Hamiltonian constraint violation during the evolution. And then if it has effects on the system. So here, this is the initial time slice. We fill the black hole interior, and then we find that most of the constraint violation is concentrated within this black hole interior. And then the blue circle marks the surface of the neutron star. And the other features that you see is because we are using here LORENE initial data, and it has a spherical grid, and we then transform it to Cartesian coordinates. So there are some features from this map. And then as the system evolves, we find that the constraint violations using the Z4C scheme, they have been decreasing this constraint violation over the evolution. And then also, maybe if you note, like the black hole size also changes, but this is like a more gauge effect. And so that's but the interesting point from this plot is to see that initially the constraints are concentrated within black hole, but over evolution, you just have most of the constraint violation at very center of this black hole. And so in this sense, we think that this conditioned excision initial data that we evolve using puncture gauge basically settles down to a puncture solution at the very late evolution of the system.
Is the constraint violation at late times inside the black hole comparable to the constraint violation that you have from just vacuum evolution? You know?
Just so you mean
So
like
suppose
just
you-
with the
Yes, suppose you had constraint
Puncture.
solved vacuum initial data.
Mhm.
Is what you get here comparable to the constraint violation that would be present in those simulations?
okay, yeah, that's interesting, but we didn't evolve any just to compare this. But yeah, maybe that's something that
makes us like that somewhere.
yeah, yeah. Or maybe talking to Mark Hannon's group, because they always they already have they could get some number. But yeah, so yeah, so this is like basically what is happening, evolving this excision initial data. And so yeah, just a few points to note here, that we have a high order extrapolation diffuse. And then the crucial thing that makes this thing that makes this happen is the Z4C constraint damping property. And then there are some other challenges which we can discuss. But the most important challenge that we face is the quality of initial data that we have at hand. And as I said, that LORENE is a very old code. So now not being maintained, it had issues in producing accurate initial data. So this will be like the motivation to move for us to move to more accurate, like Elliptica or FUKA solvers. Okay, so just few, yeah, I know I'm very
Well, we
Okay,
could finish in
close to
1
the
or 2
time.
minutes. That'd be great.
okay. Fine. So here we have some results from evolving this LORENE initial data. And basically what we find from these simulations is that even though we evolve condition initial data from excision, we find all the results that are already discussed in the literature. So we do find that the tidal disruption is dependent, highly dependent on the black hole spin, inversely proportional to the mass ratio. Then if you have low mass mergers, you can form larger disk. And also if you have highly spinning black hole, it will help in getting larger disk. And then other interesting things that we know is when we have a disrupting case. So in the tidal disruption, basically suppresses the gravitational wave emission. And this is seen here. So you can see at the end that the gravitational waves are abruptly cut off. And this is because now the neutron star has been totally disrupted. And all the matter that forms is in very small quantities, like accreting onto the black hole. Whereas if we look at high mass ratio mergers, non-disrupting case, we see that we find quasi-normal mode emissions from such systems. And then for like we wanted to also explore and see if we can find any insights into phase transition in quark core. And so for that, we evolved higher mass neutron stars, which have admit phase transition in quark core. And so overall, we find comparable results. However, like I said, LORENE, we want to cover the wider parameter of the black hole neutron star system to get a very detailed database of the system. So going on to more new solvers is like the way to do this. And here I just have a few results from the Elliptica initial data. Basically, we have good comparison again with other codes. And importantly, with Elliptica, we can cover a wider parameter space of black hole neutron star. And here especially, it allows us to have spins of the individual compact objects at arbitrary direction. And this allows us to have precessing black hole neutron star systems. And these systems will be also interesting to study because when there is tidal disruption in this kind of a system, you will have a full 3D distribution of this ejected and disk. And then the kilonova community should model this kind of signals coming from this such a 3D morphology of the ejector and the disk. Then with such new codes, we are able to also go below 10⁻³ in orbital eccentricity, which is again important aspect to think about when we want to develop accurate gravitational waveform models for such systems. Right. So this is my final slide. So I think I will move it. So here there are some results from the FUKA initial data solver. And like I said, that this is a very new publicly available solver. And so among the 3 solvers that I'm talking, this is like more the robust and fast solver because it is NPI parallelized. And then also has a wider parameter coverage. So we can use initial data with covering many extreme regions of the binary space. So importantly, what we are currently doing is evolving a primordial black hole neutron star system. So here the black hole is subsolar mass, where exactly it's 0.5 solar masses. And then we have a typical neutron star of 1.4 solar masses. And here is the waveform from that simulation. And at the bottom, I have a movie from the same simulation, basically. This here shows the unbound matter density, the bound matter density. And then here we have a geometric quantity just to see the locations of the compact objects. So here, I mean, apart from using primordial black hole in or its application in dark matter, especially black hole neutron star simulations of primordial systems are interesting because here one expects a lot of tidal deformation of the neutron star, and the gravitational wave signal coming from this can then help the gravitational wave community, where they can improve their tidal model of the neutron star to develop more accurate, even for binary neutron star cases, not just for black hole neutron star cases. So in that sense, these simulations are also useful in that sense. And then, yeah, I mean, like Elliptica, this also has the capability of reducing the eccentricity to below 10⁻⁻⁻². And then in this particular case, we find 2% disk mass of the solar mass, and then 5% of solar mass as an unbound matter from this. Okay, so these are some. Okay, yeah. So basically, I'm done. Like, this was my last slide, and yeah, I mean, okay, just leaves few points that you can take home from this talk. Thank you.
Thanks very much for the talk, Vivek. So now, do we have any questions?
So you said early on that you're interested in tracking the ejector accurately, and I guess that also just includes generally like the formation of any accretion disk. But the numerical methods that you have are basically still just like box-in-box mesh refinement, right? So you don't have true adaptive mesh refinement here. Is that a limitation? Like if you have a ejector which is traveling out rapidly, doesn't it just mean that you need a really huge, really high resolution box to cover everything, even though ideally you would have?
Right. Yeah. So the point is that once the matter is ejected, it's going to go through all the coarser levels of the grid. So from the NR side, we want to have accurate estimate of the ejected matter, how much it is, and to also say if it is like depending on the resolution, also still agreeable, because most of the time you find like even 50 to 100% differences in the amount of ejected matter just by changing the resolution. Now, to model this ejected matter in terms of kilonova signals and electromagnetic counterparts, I mean, if we want to have such infrastructure within the NR code, then yes, what David said is to be able to finally resolve this ejected matter is crucial. However, what we are aiming for is to collaborate with people who already have other codes which take the amount of ejected matter, its velocity distribution, and then they really make the model of the electromagnetic counterparts. So in that sense, we are just interested in the matter that is ejected at early on times and don't have any interest in really seeing how they evolve.
And they would do like how they would type of simulation.
Right. Yeah, exactly. Yeah.
Just calculate with an AMR code on just for the hydro part.
Yeah. Yeah. Yeah, that's the idea. I mean, in one project that we pursued with Stefan is that we take this grid-based ejected matter and then translate it to particles, and then have it evolve on such a Cowling approximation. Yeah. So for now, yeah, I think it's not like a major problem, like having this adaptive mesh for the ejected matter as well. But yeah, I mean, it'll be good to have. Yeah.
The question for you many of these simulations use them to test the equation of then you smash it up where the density and temperature could be the same, or could come spacing, which I don't know if the equation of state is valid. Can you?
So, can I mean, I didn't get the question.
Well, the question you could be this equation, and that is so dramatic that the equation of state will use the validity in the same equal to density and temperature very different. That's like this is taken. I think outside we talk about phase transition.
Right. Yeah.
Can you comment a little bit about this?
Yeah. I mean, there are some challenges with respect to simulating these systems because, as you know, that if you just look at this pressure versus density plot of
Yeah,
the
you show the plot, look, 10 minus 5 and 10 even more.
Yeah. So with phase transition, you're going to have a region of this which is going to be like having zero slope, and because you're going to use also have first derivatives for the sound speed. So currently what we use in the simulations is like a piecewise polytropic model. I mean, at least in BAM, there are some groups that do use tabulated. So what can happen is that even though there is in reality no discontinuity apart from the phase transition, which will be a discontinuity, we will still have problems in these simulations because we don't have this continuity in sound speed. So that is a way to like work that out, and it was shown by Mike Boyle. So basically, they propose a way to model this equation of state where we do not add on any discontinuities just because we are doing a piecewise polytropic model. And then once we have that, then we can study phase transitions within NR simulation, because then we are sure that whatever discontinuity or shock that are formed from the phase transition is just very natural, or the description of matter itself. So now if I come back to your question, so you said that in these simulations, the densities can increase very high, like 10^15 grams per second. So your question was if there's...
Well, yeah, more or less. I mean, I get very
right.
You are completely 10% and basically one flash in certain environment. But the same, the interesting thing is that in the bottom line, your description, let's say the real question of state is that it goes without. But it's interesting because even with this model, you are already able to rule out some question of state.
So yeah, I mean, currently we look at the bounds that are given from the detections, like what has been ruled out and what has not been, and then just use those. But for these phase transitions or quark code, because there is really no say currently from observations, we are now trying to do all sensible cases to just have it in the database in case one detects.
Okay.
Thanks.
Last week we had a talk by Shibata from Max Planck on this subject. Do you compare your simulation to the simulation of?
Oh yeah. So if I go back. So yeah, basically this is CENTRA is the code that is like belongs to Masaru Shibata and his group.
Oh, yeah, Shibata.
Yeah, and so this is a code comparison of BAM with their simulation of the same system, but using very different initial data. Mm-hmm. Yeah.
And the nuclear physics is completely not follow the same way. In both
the nuclear physics.
For instance, but you don't
Right.
have
We don't have that. So
But you got different thing in the beginning.
yeah. Yeah, so the reason is that different initial data, since like this when we set up a compact object merger system, we start at some separation. So if we don't start at the same gravitational wave frequency that's initially also done by the other group, we are going to start at a different time of the same system. And so one has to like do a realignment to see that the results are compared. And that's the that's the difference you see. That we, in BAM, when we started the run, it was at a different gravitational wave frequency to start with as compared to run. So yeah, I didn't mention that, but this window shows this realignment window. So it's the same for any code, because unless we go and start the simulation at the same initial gravitational wave frequency, we are not going to. We always will have to do this realignment of the system.
Do they use a different approach to the stuffing?
You mean the S-axis?
Well, the SACRA or
No, okay, so maybe again. So the
SXS are not doing the stuffing. So
Yeah,
I guess it means SACRA.
but even SACRA people are not doing stuffing because they are evolving a puncture initial data. So they have a black hole which is a puncture initial data, like a puncture black hole with a neutron star. But they don't have any excision initial data there. So they are evolving different initial data than SXS and also compared to us. So the point of this these two plots is to show that even when we start with different initial data, we still have comparable results. Yeah.
More questions? Maybe it's time for a very quick one. Okay. Okay. Actually, Diogo will raise his hand maybe.
Gravitational waves. What exactly do you choose to make them?
Like this,
Yeah,
just the gravitational waves. So we have this psi4 formulation of extracting the grav. So this is a Newman-Penrose formulation, and this is a scalar which captures the gravitational wave frame. And so this is just that. So this is just the real part of that. Yeah. Good. Yeah.
Any other quick comments? No? Okay, then let's send our speaker again.
If you enjoyed the video, like and subscribe.